Hi everyone, my name is Jesse Deffler and I thank you for joining my presentation today on eutrophication and the formation of dead zones. We'll start by taking a look at eutrophication, or the process in which the environment becomes nutrient rich, leading to an increase in plant and algae growth, and how this can lead to the creation of a dead zone. While we may initially think surplus nutrients in our water bodies may be a good thing, the results can be quite bad. Areas that receive these nutrients see an increase in the growth rate of phytoplankton, which in turn causes an algae bloom and a lack of oxygen in the water. We'll get more into the specifics of how this occurs later in the presentation, but the end result is a dead zone, an area that cannot support marine life. We have a dramatic increase in dead zones over the last 50 to 60 years, with approximately 415 of these areas in the world, the majority of which can be found on the coasts of the United States, mainly the East Coast, the Baltic states, Japan, and Korea. According to the Smithsonian Environmental Research Center, only about 10% of these dead zones occurred before 1950. So what causes eutrophication? Well, you may not be surprised to learn that the main cause is human activity. Specifically in developed nations, large agriculture is a massive problem in terms of eutrophication, and one that is extremely difficult to solve. After all, agriculture is the reason we have the food that we eat readily available in the United States for the most part, with cattle, corn, and soybeans being its top three products. With 2 million farms, the farming industry in the United States contributes more than $100 billion to the U.S. economy and over $1 trillion to the U.S. gross GDP. Now, if it were to be treated as its own country, U.S. agriculture would be the 16th largest economy in the world. Within the agriculture industry, fertilizer is used to increase crop yield, specifically nitrogen and phosphorus-based fertilizer like manure. What happens is these fertilizers are applied to agricultural grounds to boost plant growth. Nitrogen is typically used to increase vegetation growth, giving higher growth rates, yields, and quality of product. Phosphorus is used to aid in root development, crop maturity, and seed production. When runoff occurs during storm events, these chemicals are then carried to water sources like streams, with manure being the primary source of nitrogen and phosphorus to surface and groundwater. In developing countries, we see chemicals being added to water bodies from less regulation surrounding sewage and industry, with waste left to flow into water bodies or being simply disposed of into creeks, rivers, lakes, or the ocean, adding additional nutrients. I've included the graph on this slide showing the use of nitrogen in green and phosphorus in red in the UK in the past 100 years or so. While manure has been used in farming for centuries, industrial farming like we see in developed nations today is much more modern. Notice how steep the rise in the use of these chemicals is, and while this has gone down over the past few decades, these numbers are still much higher than they were a century ago. Okay, so on to dead zones and how they form. While eutrophication is the process in which an area becomes nutrient-rich, a dead zone is the end product of this process. As we discussed in a previous slide, excess nutrients are secreted into waterways by runoff during storm events, eventually ending up in a water body such as a lake, bay, or coastal waters. Nutrients like nitrogen and phosphorus feed the growth of algae on the surface of the water. With the influx of additional nutrients, this growth is amplified until the algae forms a thick layer. This is referred to as an algae bloom, which blocks sunlight to the water beneath it and begins deoxygenating the water. The photo on this slide shows a boat moving through an algae bloom on Lake Erie in 2013. The algae is so thick here, without the boat, we may actually think that this is just a grassy field. So as this algae begins to die off, it falls to the bottom of the water column, and here bacteria begins the decomposition process, an oxygen-intensive activity that is quite natural. However, with an increased amount of algae decomposing, an increased amount of oxygen is being used until the water becomes hypoxic. A dead zone is formally defined as having dissolved oxygen of less than 2 milligrams per liter of water. This lack of oxygen, along with an algae bloom blocking sunlight, creates an area where marine life simply cannot survive. Organisms die off or vacate the area if they're mobile enough, like fish. The water body has now become a dead zone, a biological desert with levels of oxygen too low to support life. Again, these areas are mostly found downstream of major cities and farms, and about half of dead zones are seasonal, occurring mostly in the spring and summer when temperatures are warmer, increasing algae growth, and storms are more frequent, increasing runoff. We see here a picture of Narragansett Bay in Rhode Island with thousands of mussels washed ashore. And underneath the water, researchers actually found billions more in what they describe as a local extinction event caused by a dead zone in the bay in the summer of 2001. As a result of sea life being killed and algae-cloaked waters, U.S. dead zones are estimated to cost the seafood and tourism industries approximately $82 million a year. Which brings us to our next topic, dead zones in the United States. The Gulf of Mexico is home to the largest dead zone in the United States and the second largest in the world, second only to that of the lower Black Sea. While the Black Sea dead zone occurs naturally, the Gulf of Mexico dead zone is mainly the result of runoff into the Mississippi River from the 31 states that are connected to it. Rain and melting snow wash nitrogen and phosphorus from lawns, sewage plants, and agricultural fields throughout the Midwest into the Mississippi, where it eventually ends up in the Gulf of Mexico. Last year, the dead zone measured over 3,200 square miles in size and had a 5-year average size of over 4,200 square miles. This is about 2 times larger than the management targets set by the Mississippi River and Gulf of Mexico Watershed Hypoxia Task Force. The largest Gulf dead zone was recorded in 2017 when it reached a size of 8,776 square miles. The photo on this slide shows the 2022 dead zone by color scale, with red areas showing hypoxic zones, again, where dissolved oxygen is 2 milligrams per liter or lower. It's worth noting that while the 2022 Gulf of Mexico dead zone was much smaller compared to recent years, 2021 saw a zone of over 5,300 square miles due to wind and storm events causing higher than normal discharge along the Mississippi River. The graph on this slide shows the area of the dead zone for every year since 1985, along with the 5-year moving average. The line along the bottom of the graph is the target set by the task force. Part of the EPA, the task force has set the goal of decreasing the 5-year average of the Gulf dead zone to 1,900 square miles by 2035. The Chesapeake Bay dead zone was one of the first identified in the 1970s and measures 1.2 cubic miles on average during the summer, although trends show the zone getting smaller over the long term. The main factor in the eutrophication of the Chesapeake is nutrients from runoff on the Delmarva Peninsula on the eastern side of the bay. This area is home to chicken farms that produce a large amount of manure, inundating these waters with high levels of nitrogen. Dairy farms and cornfields in Pennsylvania to the north also add nutrients to the bay through runoff. Interestingly, the western edge of the bay houses factories and urban areas that are adding to the issue. These areas emit nitrogen into the air that is then absorbed by the water, and this accounts for about 1/3 of the total nitrogen entering the bay in any given year. The Chesapeake Bay Foundation was created in 1967 to improve water quality and pollution runoff into the Chesapeake and has monitored its condition since that time. While the dead zone has shown signs of decreasing, these trends still show that mandates set by the EPA surrounding the bay's levels of oxygen, nitrogen, and phosphorus will not be met by 2025. So there are a few solutions for eutrophication and dead zones, most of which are best implemented alongside others. For instance, we can dredge a body of water, which is easiest in a lake, essentially removing the topmost layer of sediment that is the most nutrient-rich. By removing these nutrients, we help to stop the overgrowth of algae. However, this process can be somewhat expensive, and most importantly, if we aren't decreasing the amount of influx of nutrients at the source, it will have to be done on a frequent basis. The same goes for other strategies such as adding oxygen into the water through mixing and pumping, and adding aluminum into water to deactivate phosphorus. These techniques are not only expensive and complex, but they are done after there is already an issue. Oftentimes, the best solutions are also the most obvious. In this case, that we have to solve the problem of eutrophication at its source and decrease the amount of nitrogen and phosphorus that ends up in our waterways. Again, the best way forward here is to employ multiple means of decreasing runoff on farmlands. First, we must encourage practical and efficient nutrient adoption techniques by applying fertilizers at the right time of year, in the right dosage, and at the right place. Even with these techniques, runoffs will still be inevitable, and we must also employ ways of decreasing the amount of this runoff reaching our waterways. A simple example of this will be the planting of field buffers, such as trees that help reduce soil erosion while absorbing and filtering nutrients before they reach a water body. Along these lines, crop covers or cover crops can be planted year-round to reduce bare soil and soil eroding into waterways. The improvement of farm drainage systems can also be a solution to eutrophication, albeit a more expensive one. Here, farmers will manage the movement of water in fields more efficiently, redesigning operations and modifying drainage ditches to reduce nutrient load while still adequately allowing for crop draining. They can also quite simply introduce rain barrels, like the ones we see connected to a house on this slide. These collect rainwater during storm events and reduce runoff. So as discussed, solutions to eutrophication often begin on farms, reducing the amount of nitrogen and phosphorus that enters our waterways at the source. However, these solutions can be expensive, especially more complex ones like reconstructing a drainage basin. Even the planting of trees, while simple enough, costs money in an industry that already has an expensive overhead. We see this reflected in legislation on the issue, which largely revolves around grants and funding to farmers to help ease the cost of the implementation of these techniques. So the Agricultural Improvement Act of 2018, also known as the 2018 Farm Bill, provided $300 million a year in federal funding for farm conservation practices. Included in the bill was a pilot program referred to as Clear 30, CLEAR standing for Clean Lakes, Estuaries, and Rivers. It enrolls landowners in 30-year contracts that state they will maintain their land according to guidelines to reduce nutrient loading while compensating them over this time period. We may remember the Inflation Reduction Act that was signed in 2022. It increased funding to the Mississippi River and Gulf of Mexico Hypoxia Task Force, providing $60 million in grants over 5 years to implement practices included in the task force 2008 action plan. These included incentive programs for the reduction of nitrogen and phosphorus on farms, the funding, development, and implementation of water quality plans for the watershed, and the development of more efficient and cost-efficient conservation and management practices. The funding will also help the task force track these practices and evaluate their effectiveness. Finally, back in 1972, the Clean Water Act established the structure for discharge of pollutants, putting limits on discharges and nutrient loading into water bodies. It also established credit trading between states, allowing for an area that is discharging too many nutrients to purchase pollution credits from another area that has reduced its discharges more than required. And just some discussion questions for the class here. How is climate change expected to influence eutrophication and dead zones? Have we already begun to see this change? And if so, what are the implications? And the Black Sea is home to the largest dead zone in the world. What differentiates the zone from the others we discussed, and how is it formed? So thank you for listening to my presentation, and I hope you learned something about the eutrophication process and the creation of dead zones.